Uh, can everybody hear me and see the slides? Yes, okay, but okay. Mm, just let me just confirm something that recording is working properly. Okay, so uh, last time we were basically talking about our port programming. Thank you for confirming. So we were talking about programming the I/O ports of the microcontroller, and for that we had seen certain registers. For example, we had seen that there are at least on at Mega 328P there are three ports: port B, C, and D, and port C is 7-bit wide. All other ports are 8-bit wide, and then we saw how we can program the those ports in both input mode and in the output mode. And if we program them in output mode, then in what particular register we need to load the data which we need to present on the physical pins. And similarly, if they are programmed in input mode, then from what particular register, which is basically pin register of every port, from where we can read the data which is placed on the external input pins. And then we also talked about how to enable the internal pull-up registers when a port is configured as input mode, in input mode, right? So, but all the instructions we saw there, they were considering one single port as a whole, as a single entity. So there were we didn't see any instruction which can basically configure one pin of a given port in input mode or output mode without affecting any other pins on the port. So today we are going to have a look at some instructions which allow us to uh, 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 wait a minute. I think last time did we have a look at the set bit and clear bit uh, instructions? Let me check. I don't remember. So yeah, we had these. We covered these instructions, right? Set bit instruction, set bit in IO register and clear bit in IO register, which basically, let me just quickly recap. So in set bit IO register instruction, what we can do is that we can specify the bit number of a specific register, and we can set its value to 1. For example, here, if we are saying SBI port D0, so we are effectively asking to set the uh, pin to set the pin 0 of port D in input mode, sorry, in output mode, right? No, actually sending one, writing one on only single bit of this port D register, right? Remember, this is not data direction register, but the next register, data direction C register. So here we are saying set uh, pin 5 of port C in output mode. Okay. So these instructions, SBI, it allows us to set one particular bit of a register to value of 1. Uh, to complement it, we have another instruction, which is clear bit in IO register. So it allows us to do exactly the opposite, which is basically it allows us to clear to set the value of a bit equal to 0, but only for a single bit in a register. For example, let's say if we want to configure the pin number 5 of the port C register in input mode, so we can say, okay, clear the bit number 5 of data direction register of port C, right? So we had seen these instructions. Now let's move to the today's lecture. So today we are like going to cover two with respect to the port programming. We are going to cover two very important instructions, which are skip if bit in IO register is cleared, and skip if a bit in IO register is set, right? So what does this instruction mean? It basically says that check the, let me select the pointer. Check this check the bit at this particular index of this given register, and if this bit is cleared, then in the program sequence, whatever next instruction you have, skip that instruction, don't execute it. So it is again kind of branch instruction, But instead of checking any flag in the status register, you are basically checking a bit of a given register, the value of a bit of a given register. If it is equal to 0, then you skip the next instruction. If it is not 0, then you don't skip it, right? And here is the syntax. So the first operand is basically your register, and the second one is the index within that register. And this is your instruction format or machine code for SBIC instructions. Skip if bit in a register is cleared. The register can be any general purpose register from register 0 to register 31. And since all of these registers are 8-bit wide, that's why the index you specify, it can be either, it can be in within range of 0 to 7, both inclusive. So here is an example. So when we are saying SBIC or skip if, let me name it as SBIC because this is like a long name. I don't want to say it again and again. So SBIC port D0. So here basically I'm saying check the bit number 0 of port D register, and if the value of the bit at index 0 is 0, then skip the next instruction, which is increment. So this instruction will not be executed, and program counter will go to the load immediate instruction, but only if the value of the bit at index 0 in port D register is 0. But if it is not 0, then this instruction will increment instruction, skip, it will be executed. Okay. Uh, to complement SBIC, we have another instruction, which is SBIS. It does exactly opposite of SBIC. So it skips the next instruction if the bit at the given index of a register is set equal to 1. So, and here is the syntax, similar syntax, only difference is the name of the instruction. So the first operand is here the register, and B, the second operand is the index of a bit within that register. And again, definitely opcode is different as compared to SBIC, but restrictions are same. Like A can be any register, any general purpose register from 0 to 31, and B can be any value within that 8-bit register. So ranging the index value ranges from 0 to 7. So here, if we say SBIS port D0, so here we are saying check the value of the bit at index 0 of the port D register, and if the value of that bit is 1, then skip this next instruction, this one. But if this is not 1, then if the value of the bit at index 0 in port D register is not 1, then increment instruction will not be skipped and will be executed. Any questions? Okay. So here is an example. Let's say we want to write a program to perform the following operation. We want to keep monitoring the uh, port B2, which basically mean the physical pin of the physical pin number 2 of port B. We want to monitor it and until it becomes high. So basically it means like we are configuring this pin definitely as input. That's why we are monitoring it. So when the external input on this pin becomes high, so until that point we wait. But once it is high, then the PB2 becomes, when PB2 becomes high, we need to write the value of 45 to port C and send a high to low pulse to port to pin D3. So we need to write this value of hex 45 to port C. So which means that we need to configure port C in output mode, right? And then we need to send a high to low pulse to pin number 3 of port D. So which means like the pin number 3 of port D is also configured as output pin, right? So initially we send a high signal on PD3 or pin 3 of the port D, and then we keep monitoring the pin 2 on port B, and when we see a high signal on this input pin, then we send a low output on PD3, and also we send hex 45 to port C, right? So let's see how we can write this program. So first, we need to set the port B, pin 2 of the port B in input mode, right? So, but for that, we are not going to write the whole data direction register, right? Now we have the knowledge of CBI instruction, which is like clear the bit in IO register. So since we need to configure the pin number 2, that's why we are saying set the bit at index 2 of data direction register B. Sorry, not set, clear it. So that this pin is configured as input pin. If you have any question or if you think I'm not clear, let me know, okay? Yeah, don't hesitate. And then remember we said that if for the purpose of stability of input signals, it's always advised to enable the pull-up registers. So whenever a pin is configured as input mode, then the port B register is used actually to enable or disable the pull-up registers. So since we are like manipulating only pin B, that's why we are saying that set the bit at index 2 of the port B register equal to 1. So basically we are saying enable the pull-up register on that input pin. Then next thing is that we are going to make the port C as output port, but whole of the port, not only a specific pin. So we are writing 0xFF in R16 load immediate, and then we are sending R16 to data direction register of port C. Now all the pins of the port C are registered in configured in output mode. Again, we also need to configure this PD3 in output mode, but only one single pin, which is pin number 3 on the port D. So which means that we only need to write one in the data direction register of the port D. So in the bit 3 of the data direction register of port D. So we are saying here that set the bit at index 3 in the data direction register of port D equal to 1. Set bit in the IO register. Okay, so after once we are done with configuration, so we have now configured port PB2 in input mode, port C in output mode, and PD3 in output mode. So now what we need to do is we need to monitor the PB2 input, right? So which basically, okay, before going there, before having a look at the code, so what we need to do, we need to monitor the PB2 until it becomes high, right? So if it becomes high, then what we need to like send 45 to port C. But if it doesn't become high, then what we need to do is that we need to go back in the loop and again check the value of the PB2. So basically it's mean that we need to construct a loop, right? So here what we are doing is that uh, skip skip if the bit in IO register is set, right? Which pin we need to monitor? Pin number 2 of the port B. So remember how we read the values when a port is configured in input mode by reading the value of the pin register. But this time we don't want to read all of the 8 bits of the pin register. We want to read only one bit at index 2 of the pin B register, right? Pin register of port B, right? So if we read it and we check if it is high or not. If it is high, we are saying that skip the next instruction, right? So basically and if it is not high, then this instruction will not be skipped. So let's say that the input is not high, it is low, right? So if input is low, then this instruction will not be skipped, it will be executed. So if it will be executed, we are saying relative jump back to again. So there will be a loop here, right? As long as this input is low, because we are saying skip only if the input is high. So now if let's say if external input is high, then this instruction jump again, the instruction will be skipped, and then we will have the rest of the program, which is basically doing what we need to do, which is basically put the 45 in R16 register and then write the value of R16, which is 0x45 on port C, and then also send a high to low signal on port D on the pin number 3 of the port D. So first you are setting it to 1 by saying set bit in IO register at index number 3 of the port D, and then you are saying clear it. Actually, it will be more meaningful if we simply move this instruction. Let's say this instruction, if we simply move it before the loop here, because otherwise like the microcontroller is operating at very high frequency. So being a human, we will not be able to differentiate between the high and low. Like it will be like very fast. Okay. So here what we can do is that before entering the loop, we can set the port D register, sorry, the pin number 3 of the port D to high, and once we detect a high signal on PB2, then we can send a low signal on this one. Actually, let me correct it right now so that when you so that you don't have a problem when you are actually going through the slide on your own. Any questions? Also here should that let me set the commit set PD3 to high, and okay. Okay. Any questions before we move to the next example? No? Okay. So here we have an example where we assume that a switch is connected to the pin PB0 and an LED is connected to the pin BB7. So you can see in the figure, we have switch here connected at PB0, so which basically means that we are configuring PB0 as input pin, and we have an LED connected with PB7, which means that this PB7 is configured as output pin, right? So now we need to write a program to get the status of the switch and send it to the LED. So basically what we want to do is that if this switch is pressed, then we will read a value of 1. And if a microcontroller senses an input of 1, it should send a 1 signal to the PP7, which will cause the LED to turn on, right? And if it reads a value of 0, which is basically when switch is not pressed, then our LED should not be turned on, right? Uh, so, uh, and remember, we don't need to like configure the whole port B, all of the 8 pins as like input or output. We want to configure pin 0 of the port B in input mode and pin 7 of the same port as output pin, right? And all other pins, they remain unaffected. So first, make PB0 an input. How? By writing in the DDRB register, but not the all of the register, only at the bits at the index 0, and by setting it to by clearing it, right? So clearing means writing a value of 0 in that bit, right? And then we are configuring PB7 in output mode. How? By writing by setting a value of 1 at index 7 of the DDRB register, data direction register of port B, right? Now what we need to do is that we basically need to monitor this pin B0, right? So what we can do is that we can skip the next instruction if PB0 is clear. So if PB0 is if the port B0 is clear, which basically mean that we are getting an input of low signal, logic low, then we continuously keep monitoring it and we don't send any output of 1 to the LED, right? So for example, let's say if the user doesn't press the switch, so input here will be 0. So if input will be 0, so this instruction is saying skip next instruction if bit at index 0 of pin B is clear, right? So if it is not pressed, it will be clear. So this next instruction will be skipped. Wait a minute. Mm, Yeah, okay, so I am just confusing this. This is not this is again. So we'll go to if it is clear, so if we get a value of 0 here, so we need to send that value of 0 to the LED, right? So and if we get value of 1, then we need to send the value of 1 to the LED, right? So here we are saying that if the value which you read is cleared, so then uh, it means go to the body of the code which actually writes 1 on the LED, which is basically our, right? So when we go to our here, So what we are doing is that we are writing the value of, we are setting the bit 7 of the port B equal to 1, right? So which means basically we are sending 1 here, and then we say, okay, go back and monitor the switch again. So we come here again, right? And now let's say the next time the bit is not clear, right? So this time the switch is closed here. The switch is closed. If switch is closed now, the input will be 1. So if input is 1, then the bit is, it means the bit is not clear. So the next instruction will not be skipped. Sorry, the next instruction, it's like a little bit confusing, right? Uh, so if it will not be clear, then okay, sorry guys, let me restart this slide. Let me try to explain from again from the start. Let me first discard the annotations. So I think the code is, everyone is clear until this point, right? Where we are only configuring the two pins in their input mode and output mode. Does anyone have a confusion before until this point? Let me know if you have a question, right? Okay, so then next what we are doing is that we are now going to monitor pin B0, and here we are saying keep checking, check the value of the bit 0 of pin 0 of the port input port B, right? And if it is 0, then skip the next instruction, right? So if it is 0, so we are skipping the next instruction, which basically mean that we want to send a value of 0 to the SPI port B7. Yeah, it's okay. So here, if the value is now here, if the value is 0, we are saying in only in that case, skip the next instruction, right? But if the value, let's say if the value is 0, now what will happen? This instruction will not be executed, this one, right? And the control will reach at this point. So here what we are saying clear the bit 7 of the port B, which are basically mean we are writing 0 at this output pin, right? And then we are saying now go back and again start monitoring the input pin PB0. Now let's say this time if the input is 1, right? So it's mean like if in, so we are saying skip the next instruction if PB is clear, but it is not clear. So this instruction will be executed and we will go to the label hour. And here we are writing value of 1 in the bit number 7 of the port B. So basically we are sending 1 on the output. I know it's kind of a little bit confusing, because why it is confusing? Because of the same thing which you remember, which I mentioned when we were talking about branch conditions. So at a higher level language or at a higher abstraction, when you are thinking, you think in for example, if you say if x is greater than y, then take a jump. But when you convert it into assembly, so you use the opposite of the condition in the assembly program. So instead of saying if x is greater than y, you say if x is less than or equal to y, then take the jump. So same, so it is issue with the thought process. Otherwise, the code is correct. The code is correct. Okay. If you have any question, please let me know. I can explain it again. No. Okay. So before we start with our next set of slide, which basically talks are about today's set of slide, which talks about jump and call instructions. I just wanted to share this information with you that I have uh, released what is this called? 6-week early performance grades for this course. I already made an announcement on the Canvas page, and this grading is based this 6-week early grading is based on quiz 1 to 5, lab 1 to 2, and homework 1 to 3, right? So the absolute points for these three, these all of these SS items together is 15.5. So if, like, for example, you have, let's say, you have absolute points of 15.5, it's mean you got A plus, right? Which is 100%, right? And then if you have something others, points other than 15.5, less than 5, I have shared with you the grading table. So that table is used to determine your letter grade. But again, this is just for your like self-awareness, that where you stand at this point, when we are like, this course is still in progress, right? We are six week into the course. So it tells you whether you need to, like, how much more effort you need to put to get a better grade, or already you are on the high end of the grade scale or not. Okay. So I have entered those grades on banner today, but I think they will be released to you. I don't know when, but not at least today. Okay. Okay, so let's talk about this jump and call instructions again. This is like a kind of, always mismatch happening between what we are doing in the labs and what we are covering in the lectures. Because the thing is, like, if we wait for the labs until we have covered all of these instructions, it's difficult to do all the labs within like 4 months, or like how many weeks we have, like 16 weeks or 15 weeks. So that's why we have to, like, in lab, so we have to, like, go a little bit ahead of the lectures. So we have already been using these instructions in the labs, like jump and call, but we haven't discussed them in detail. Like, you have some idea of how jump work and how call work, and like in last lab, when I was preparing the discussion, I tried to give you a somewhat explanation of how call works and what is the stack, but we never covered it in our lecture. So we are going to do that today now. Okay. So the topics we are going to cover are like the jump and call instructions, and how stack is involved, or how stack is used when we use the call instruction, and what how we can call a function in assembly language, like how, for example, the main function can call or let's say foo function can call the function bar, and bar can call the function foo, right? How can we pass the parameters, and how can we return the values in assembly language? Okay. So the thing is, like, if we don't have these instructions like call and jump, actually we have also already seen the jump, one version or one flavor of the jump instructions, which are like conditional branches, right? Those are also the jump instructions, depending upon on condition. If the condition is true or false, you take a jump or not, right? So if we don't have these instructions like call, conditional jumps, or unconditional jumps, then our program will execute only in a linear fashion. So which basically mean that all the instructions, they execute one after the other. So for example, if you have a look at this code snippet on the right, uh, first A is equal to B plus C will be executed. Definitely it is a higher level language program. Let's say C. And then the next statement, C is equal to C minus 2 will be executed, and then D is equal to A plus C. The program is executed in sequential fashion or sequential order, right? But uh, this is not how all the time real life programs work, because we need to make decisions in the program based on certain conditions, right? So if there is no possibility to divert from a sequential execution, then we cannot make the decision in assembly language programs, or any language, even if it's a higher language, right? If there is no possibility of doing nonlinear program execution, you cannot write meaningful programs. So for nonlinear program execution, what we need to do is, like, we use conditional instructions. For example, if statement in higher level languages, or we have loops like for loop or do while loop, or a while loop, and we also make function calls, right? Now the question is, how can we do the same thing, like writing if statements, are writing a loop or making a function call in assembly language? So Here is an example in higher level language where we are using the if statement to decide the flow of our execution based on a condition. So initially, like you are setting two variables, a is equal to c is equal to 3, and then you're checking the condition. So if a is equal to 8, so if condition is this condition is true, then you will say go to the line number 6, otherwise you will go to line number 8, right? But in this case, definitely condition is false, so we'll go to the line number 8. Uh, Similarly, in loops, what we do is that we again don't have nonlinear execution, and we go back in the execution sequence for a certain number of time depending upon a condition. So, for example, here we are setting c equal to 0, a is equal to 2, and then we are checking the condition if a is less than 4. Then we enter the body of the loop, and then we increment a. So a will become 3. We will do another execution and set c equal to c plus a, and then increment a, and will become 4. Now the condition will be false. That's why we'll go to the next statement. So why we are like having a why we are looking at these slides, just to like refresh our memory how nonlinear execution works in the higher level languages, right? And function calls. So let's say you have a main function, and other than that main function, you have an other function which is named as function one, right? And you are calling function one in the within the body of the main function, right? So so if you make a function call, so what will happen, that control will go to the line number 8 instead of like line number 6. It is not linear anymore. So once you are done with the execution of the body of the function one, then the control goes back to the next statement in the main function after the line where you had where you made the function call, basically line 6, right? So in our AVR assembly language, we have two group of instructions that can carry out nonlinear program execution. One is jump and the other are call, right? And within the jump, again, you have two sub categories or subgroups. One are like conditional branches, conditional jumps. Another is the unconditional jumps. So for example, branch not equal, it is also a jump, but it is a conditional jump. If the condition is true, then you will take a jump. Otherwise, you will not take the jump. However, there are the other instructions like jump and relative jump. There is another one, I jump or indirect jump. So these instructions, they don't check a condition. So these jumps are always taken. And then for making the function call, we need a set of two instruction call, which basically is clear from its name that it is used to make a function call, and return is an instruction which helps us to return back to the caller once we are done with the execution of body of the callee function, or the function which is being called, right? So let's have a look at jump. So jump instruction, it is also as known as absolute jump. And how it works, that it changes the program counter and causes the CPU to execute an instruction other than that the next instruction. We will see an example, so it will become clear. Actually, the program counter is loaded with the value of the operand which is provided as part of the jump instruction, right? And as a result, what happens that definitely when you are changing the value of the program counter, so the next instruction that will be executed will not be in sequence. It will be the instruction at the address which is loaded in the program counter, right? Uh, So as I said, there are two type of jump instructions. Let's first talk about these conditional jumps. So these they jump after checking a condition. So if the condition is true, then the jump is taken. Otherwise, the next instruction, the sequence is executed. For example, branch not equal, or branch if carry is clear, or branch if carry is set, or branch is uh, 0, branch if same or higher, and so on, right? We had a look on all those instructions earlier, right? But today our main focus is basically on unconditional jump instructions. So these instructions, they jump unconditionally, with which basically mean that they don't check any condition. So whatever target location you give or you specify, the jump is taken to that target location. And there are like three jump instructions: R jump, jump, and I jump, or indirect jump. So, uh, how they work. So let's have a look. We will discuss these instructions individually, how they are different from each other in next slide. But the general syntax is the general approach is the same. What you do is that you label the location to jump to, and using a unique name. For example, if you want to jump to this location, which is basically the instruction number 3, you will give it a label, and which will be followed by a colon. Again, it should be a unique label, which basically means there should be no label in your program with exactly the same name. Otherwise, your assembler will complain. Uh, and then when you will execute then jump instruction, so your execution will jump to the label. So for example, when this instruction will be executed, R jump L1, so the next instruction after instruction number 4 will not be instruction 5, it will be instruction number 3, right? Okay, so how these 3 instructions differ from each other in the way how we specify the target address, right? So in jump instruction, the target address is specified as an operand of the instruction itself. In our jump instruction or relative jump instruction, uh, again, we have an operand as part of the instruction itself, but then that operand is added with the value of PC plus 1. It is same as you remember what was this instruction we talked as like conditional branch instructions, right? So in conditional branch instruction, how the target address was calculated by adding offset to PC plus 1. So same here, we simply add operand, which is basically an offset to PC plus 1, and that's how we calculate the target address. But in jump instruction, we are not adding operand to the PC plus 1, we are simply setting PC equal to operand. And in iJump instruction, what we do is like uh, we first load a value in Z register, which is 32-bit register. Actually, it is combination of two 8-bit register, and collectively they are named as in the combined form as Z register. So we load a 16-bit value in that Z register, which is treated as an address. But when we execute iJump, so the value of that Z register is placed in the PC. So then the next instruction will be executed from the address which we placed in the Z register. Okay. And the other thing is like this jump instruction is 4-bit wide. So it's sorry, if you look at its machine code, it is 4 byte, not 4-bit. 4 byte. It is 4 byte wide, and the remaining two, R jump and I jump, both of them are 2 byte wide. So, any questions? No. So let's have a look at jump instruction now. So when you say jump, then after that, basically you specify the label of, I don't know if you have an example here. Uh, yeah, here we have example. So after writing jump, you specify the label, and label basically is the target address. So what happens is that PC is set equal to that target address, which we are naming here as operand. So now if you look at its machine code or instruction format, so you can see that there are 22 bits which are basically used to specify the target address. So these bits which have fixed value 1001, they make the opcode, and all other bits which are indicated at x-axis, they are 22 in bit in total, and you can use them to specify a 22-bit long address, right? So here is an example. So this is these red color bits, they are actually opcode, and then remaining bits make the operand. So basically we are saying go to the address in memory, like next execute the next instruction from the memory which is located at address 110. So I mean you can do the math. So it will be 1, 2, 4. So basically it will be 6. So the next instruction will be executed from address 6 in memory. Okay, now here we have an animation which actually helps us to understand how this jump instruction works. So let me first break down this rectangle or this code on the right side. This column basically gives you the address of the address of the memory location where these instructions are stored. On the right, you have the code. Here we have the PC register. For this particular instruction which is located at address 2, we also show the machine code because it is of our special interest. And then also we have the machine code for this jump instruction, right? So we actually break it into opcode and the operand, right? So how we get the operand and opcode just by calculating the values of these bits. Okay, so initially your PC is 0. So when PC is 0, your first instruction that is executed is this one, load immediate 15 into R16. After that, PC is incremented in like linear fashion, so it becomes 1. And the next instruction that is executed is from the address 1, which is load immediate 5 into R17. Then after that, again, PC is incremented, so it becomes 2. So next instruction executed is jump label name. Now, this is interesting. So because remember, when we say jump label name, what happens? That PC is loaded, PC is set equal to the operand, right? And that's why what we have done is that we have uh, converted this instruction into the machine format, machine code. So when you look at the machine code, the operand is 006. So what will happen now that PC will be, after the execution of this instruction, PC will be set equal to 6, right? So it's mean that now the next instruction that will be executed will be the instruction at address 6, which is this add instruction, right? Add R17 to R16. And after that, again, program counter is incremented by 1. So the next instruction executed is in sequence. Again, it is a jump instruction. So when this instruction will be executed, the PC will be loaded with the value of the operand. And if you look at this machine code of this instruction here, so the machine code is written here again. So what will happen that this will be again moved 006 to the PC, which means that next instruction that will be executed will be uh, uh, again this instruction, and we have actually a loop here happening, right? Any questions? Any questions? No? Okay, by the way, I also released, like I guess last week, a survey for instructors evaluation. I hope you guys have responded to that survey. If not, please do so because it is important for me so that I can gauge my performance and see how I'm doing. Uh, and based on your feedback, I will try to like improve myself. Okay, so I think today is the deadline. So please make sure that you have participated in the survey. It carries no points, but I will encourage you to fill that survey form. Okay. The other instruction which we have in the category of unconditional jumps is relative jump. The why we have, you can ask the question why we need these like different instructions which are necessarily doing the same thing. All of them are doing the unconditional jumps, right? So if we have jump instruction, why we need the relative jump? The issue is that jump instruction, the good thing about the jump instruction is that this operand, let me go back. So this we have 22 bits to specify the target address where we want to go. So if 22 bits basically mean you can jump anywhere in an address space of 4 megabyte, right? So it is huge, right? So it gives you the flexibility. You can go anywhere. Like if you have a program which has 4 mega instructions or 4 mega locations, right? So then you can jump anywhere within that program. Like you can jump here, you can jump here, or you can jump forward somewhere, as long as it is within the 4 million, the 4 mega address space, right? That is good thing about the jump. But the bad thing is that it is a 4-byte instruction. So 4-byte instruction mean that so it means that it takes, like if you are using this instruction in your program, so it consumes four bytes of the memory to be stored in the program memory, right? And remember, we are talking about microcontrollers which are already which already have very low capacity of both program memory and the data memory. So it's better if like for example, if we are writing a program which doesn't need to make a jump that long, like within an address space of 4 mega locations, then we don't need to use this instruction, a jump instruction, which basically mean that we don't need to waste the 4 bytes. We can use the R jump instruction, which actually uses only 2 bytes. But so when you write the codes, now your code size is basically, if you replace the jump instruction by our jump instruction and do necessarily the same thing, so your code size is now reduced by 2 bytes, right? And these 2 bytes can become like precious when you are like running low in program memory, for example, right? So if you can save a lot of bytes by replacing all of the jumps by R jumps, then you can save 2 bytes per replacement. But the problem with R jump is, so that is the good thing about the R jump, that it consumes only 2 bytes. But the problem with it is that the range within which you can jump is limited as compared to the jump instruction. Why? Because it is 2 byte, so it has much less number of bytes available, which is basically 12 bits available to specify the address. Here you had how many? 22. So 22 means you can specify 4 million addresses, 4 mega addresses. But if you have 12, then you can specify basically 4 times 1024. You can do the math, number of addresses. But these 12 bits are used to specify a signed number. So the if you have a 12-bit signed number, its range is -204 to 2047, right? Just like, for example, if you have a 3-bit if you have a 4-bit signed number, the range is from -7 to uh, uh, -8 to 7, right? If you have 4-bit signed number. So similarly, if you have 12-bit signed number, the range is -2048 to 2047. You can calculate it how to do it. We did it in like one of our first lectures, right? I don't want to go through the those process or those steps again. So the basically the thing is like, when you execute the R jump instruction, so your PC is set equal to PC plus one plus operand, right? Now, since the operand is a signed number, so if the operand is the value is positive, so you are jumping forward. If value of operand is negative, you are jumping backward, right? This is again just like our branch instructions. If offset is positive, the branch is forward. If offset is negative, branch is backward. PC plus one is the address of the instruction right after our jump in the program memory. Again, this is same what we have seen when we are talking about conditional jump instructions. So this is the machine code here. So if you have, for example, the opcode will always remain fixed and your operand is this one. So if you convert the operand into the equivalent form, so since the most significant bit is here 0, so it's mean it is a positive number. So this is basically equal to 6. So you are saying the PC will be set equal to PC plus 1 plus 6. So it is a forward jump. Now let's have a look at an example where we are using the relative jump instead of jump instruction, right? So the structure of the example is similar to what we have seen earlier. So again, this column here shows the addresses, and on the right we have the code. Initially, our program counter is set equal to 0, and for the jump instructions, our jump instructions, we have also noted our machine code, right? So initially PC is equal to 0, so first instruction is incremented, and after that PC becomes 1, which executes the next instruction and loads the 5 into R17, and then PC is set equal to 2 here, so which is now pointing to the R jump instruction or relative jump instruction. So the only difference here this time as compared to the jump instruction is how the value of PC register is set. Previously, PC was set equal to operand, but this time PC will be set equal to PC plus 1 plus operand, right? So what is PC plus 1? It is 3, right? And what is operand? 2 here now. So 3 plus 2, so now PC will be set equal to 5, right? Yeah, so PC becomes equal to 5. So next instruction that will be executed will be from the address 5, which is again an add instruction. After executing this instruction, our PC increments and becomes 6. And the instruction we have at address 6 is again a relative jump instruction. So we again need to update the value of PC in the same way, which is basically we set PC equal to PC plus 1 plus operand, the operand of the relative jump instruction. What is the operand here? It is FFE. Remember, if you have F, it's mean that most significant bit is 1. So if most significant bit is 1, remember it is a signed number. So if most significant bit is 1, it's mean it is a negative number. So it's mean that it will be a backward jump, right? So you can convert it into equivalent decimal form to see like how many backward jumps you are taking. But I'm not going to do that at this point. So when you will add it, so you will get the value of 5. So you are going back to the this location. So now you are constructing a loop. Okay. Any questions? No? Okay. Indirect jump instruction. Uh, Again, the difference from this instruction is also 2 byte long. So it is smaller in size as compared to the jump instruction, and same in size as compared to relative jump instruction. But when you compare it with relative jump instruction, the good thing is that it allows you to jump anywhere in the program address space. But the way it allows you to jump anywhere, so the range where you can jump, where you have your target location, the range is larger as compared to relative jump. But the way it allows is like a bit complicated, uh, and I think it kills the motivation of having a 2 byte size for the instruction. Why? Because it will become clear when I will show you an example. Okay, while I'm saying that it kills the motivation of having an instruction of 2 bytes by to save the code memory, a size of your code, right? So how it works, basically what you do is that you first load your target address in the Z register. Z register is nothing but the combination of these two registers, R30 and R31. So whatever your target address is, so if you have these two registers, mean you can specify a target address of 16-bit. So this is better as compared to the RJump where we were using only 12 bits to specify the target to specify the operand, right? But here this time we are using 16 bits, so which means we have a larger range. So we uh, load the lower 8 bits of the target address in R30 and higher 8 bits in the R31, and together it is known as Z register. Now when you will execute iJump, so iJump has no operand, but you make sure that you first load your target address in these two register. But when you execute iJump, so what will happen that PC will be set equal to the value of Z register, right? So the instruction has no operand, just unlike jump and jump. So PC is loaded with the content of Z register. For example, if Z points to location 100, so by executing iJump, the CPU will jump to the location 100. Any questions? So why I was saying that the good thing is for iJump is like it is 2 byte, but then it overkills the motivation of having 2 byte, because for example, if here I don't want to use rjump and I want to use iJump, I cannot use iJump directly. I first need to put an instruction here which loads the value into R, what was that, R30? Yeah, that loads the value in R30. Then another instruction will load the value in R31, and then I call the iJump instruction. So basically, instead of one instruction, I am using three instructions. Two instructions to load the value into R30 and R31, and then iJump instruction to do the actual jump. So even if like those two other instructions are, let's say, single byte, so still in total I'm consuming 4 bytes. So it's better than I can directly use the jump instruction instead of uh, like using the jump. This is like downside of the this is the downside of iJump instruction. But the good thing about iJump instruction is that it gives you it gives you the flexibility, or it gives you the option of dynamically deciding during your program to where to jump, depending upon the condition. Let's say you have a program, and you have a loop, and in the body of the loop you have this I jump instruction. Let me go back to the go to the OneNote and explain it. We have some time still. Sorry. Okay. So let me write a program here. Uh, let's say you are putting a label L1, and then you say here, for example, you say jump, right? And then you say jump L1. And every in each iteration, what will happen? You will always be jumping to this particular label, right? This jump will always take you to this particular instruction, right? Now, let's see what happen in case of relative jump, right? So in relative jump, like let's say you have L2, let me use a different label, L2, and then you say R jump L2, right? Again, all the time you will be going back to this label. So you cannot change, like every time in every iteration you will be going back exactly at this location here, right? And same is the case here. The the s- target address is static, right? The difference between jump and R jump is basically how much long jump you can take. The range of the jump is longer in jump instruction as compared to R jump instruction, right? But how things happen, or how things work in case of uh, in case of I jump instruction. So what I need to do is that for using I jump, I first need to load the value in Z register, right? Which is basically I need to put value in R30 and R31. I'm not writing showing loading of value in R30 and R31 separately. I'm just saying load some value in Z, right? And let's say I'm saying, okay, load the value from register 5, right? In Z. And then you are saying I jump. So now where the jump will happen, what will be the target rest of the jump? It will depend upon the value of Z, which in turn depends upon the value of R5. Now let's say that this program which we are running here, uh, it sets the value of R5 equal to, let's say 10, right? So maybe, and let's say 10 is back here. So 10 is the address, right? Right? So the jump will go to the address 10. Another iteration will happen. Now, let's say this time the value of R5, due to the code we have written here, this code, the value of R5, let's say it is set not equal to 10, but let's say it is set equal to 20. So the jump will go to the address 20. Let's say next time another iteration happen, and this time the value of R5 is set equal to uh, 50, right? And maybe 50 is here somewhere. So jump will be taken to this location. So the difference here is that the target of the I jump is set dynamically, while the target of the jump and the R jump instructions, they are static. You cannot change them. They always go to the same location. But the target of I jump, it can change depending upon the value of Z, right? Is it clear? Okay. So we have covered our jump instructions. Now let's talk about call instruction. uh, are topics are things related to the call instruction, right? So what we are going to cover is like what is the stack, what is the push operation, what is pop operation, uh, how we call a function in assembly language, how we pass parameters when we're calling a function, right? So let's first talk about stack frame pointer. So what is stack? Stack is basically a data structure, and basically it is nothing but a memory location, so which is controlled by the stack pointer, right? So what happen is like stack allows you to you can place the temporary data on stack. So uh, stack is like let's say your stack data structure or your stack starts at some particular address in memory, basically data memory, let's say 0x7ff. Why this address I will tell you later, but let's say our stacks, this is the first location of our stack data structure, right? So what happens, so and then here we are assuming that our stack grows downward. I'm saying downward, but the arrow is upward. uh, why then I'm saying downward? Because our address is reduced, right? So the first address is 0x7f, and then address of the next location is 0x7fe, and then 0x7fd, and so on. So uh, that's why when the addresses of the next location in stack, if the address is reducing, then we say that stack grows downward, right? The other thing is related to the stack is a stack pointer. Stack pointer basically tells us, then shows us or point us the next empty location in the stack, right? So when we say next empty location, it's mean the location where we can place an item in the stack, right? So stack pointer, it always points to the next empty location. So actually at the start of everything, let's say if you have empty stack, so this stack pointer should be pointing to the first location here. uh, Stack pointer, it is initialized to 0x7ff to point to the largest address in 2 KB SRAM of the AVR. Okay, theoretically, what you can do is that you can set the stack pointer to any address in the data memory. So if you have data memory with a size of 2 KB, what are the maximum, what is the range of addresses? The smallest address will be all zero. I don't want to put all zeros, like, okay, let's say 0x 3 zeros, because we are writing in hexa, so with 3 zeros are enough. So the smallest address will be this one, and the largest address will be 0x7ff. You know how we are calculating this largest address, right? So if it is 2 KB, it's mean that how many bits are available. So 2 and kilobyte is 2 raised to power 10. 1 kilo is 2 raised to power 10. And so it's total, it's mean 2 raised to power 11. So if I have 11 bits, all with the value of 1, it becomes 7ff, right? So this is the maximum address. Okay. So as I said, theoretically, you can initialize stack pointer such that it points anywhere within this address range, right? But we don't want to do that. Why? Because maybe we have some data already here, and we don't want to override that data. Therefore, it's safe and it is a convention to initialize the stack pointer to point to the last location in your memory, right? So if your memory is of total size, data memory is of total size 2 KB, the address of the last location will be 0x7ff. So that's why we initialize it with this particular address, stack pointer with this particular address in this example. And the other thing is that your AVR compiler, it allocates the global variables from the smallest address 0x10. So global variables in your program, they are allocated here, or they are placed here, right? So if for example, if you say, okay, I'm initializing my stack pointer, let's say with an address of 0x100, so then whenever you will push or you will place an item on the stack, that item will overwrite whatever global variable you had in the memory at this particular address. So which means that your global variable, they will be corrupted, right? And we don't want that to happen. That's why we like to be on the safe side, we initialize stack pointer with the last address. Now you can ask the question again, like it can happen that I have a program which writes the whole memory up to the last address, right? And then if I use the stack pointer, if I initialize the stack pointer with this address, then it's mean that I'm overwriting. And if I then push any item on the stack, it's mean I'm overwriting my data in memory. Yeah, that is true. But since we are dealing with the assembly language, and then we need to be like take care of, we need to check, we need to put checks in our program to avoid that kind of situation, right? That we don't override, our program doesn't override some data which our program has already generated. So when stack is too low, it can override global data and causes serious issues, which I just said. Like if we initialize stack pointer, let's say to address of 0x100, it will override the global data. Okay. So we said that we have an item which is named a stack pointer, which is used to point to the location in the next empty location in the stack. So basically, stack pointer is a register. So, but this is a 16-bit register. Remember, in AVR microcontroller, all the registers are 8-bit. So that's why stack pointer is composed of basically two separate registers, which are named as stack pointer low and stack pointer high. Each one of them are 8-bit, but in total they make the 16-bit. So we can specify a 16-bit value for the stack pointer, right? So that it can point to any location in the memory. Any questions? Okay, let me just discard these annotations. Okay, so the stack pointer, what is the address? What is the address of the stack pointer register? So the address of SPH and SPL in memory is 0x5e and 0x5d, and in the IO address space it is 0x3e and 0x3d. Okay. uh, but you don't need to remember it. You can always refer to the slides or the book to find the address, or you can even use the name of the register directly in your instruction instead of addresses of those registers. Okay, so we said that stack is used to hold the data items, right? So the operation of operation of putting some data on the stack is known as pushing the item. Like for example, if I say I want to push a value of, let me again, so let's say my stack pointer is not pointing to this location, but it is pointing to this first location. So when I say, let's say I want to put a value of 5 on the stack, so I will say I'm pushing the value of 5. So when I say push 5, I'm not writing complete full spelling of push, I'm just writing P5. So when I'm saying push 5, or maybe I should, because then for pop also starts from P, so it will be difficult. So when I say push 5, so basically 5 will be placed here, right? And then what happens is that as a part of the push operation, stack pointer is incremented automatically. You don't need to write a separate instruction for incrementing the value of the stack pointer. So it gets not incremented, decremented automatically. So it points to next location. So first the value is placed on the location which is pointed by the current value of the stack pointer, and after pushing the value, the stack pointer is decremented. So now it will be pointing to the address 0x7fe, right? And now when you will say push, let's say 4, so 4 will be placed here, and stack pointer will now point to the next empty location by decrementing the value of the stack. So it will become now 0x7fd, right? Sorry. So the process of putting a value or placing a value on the stack is known as push operation, and the process of removing a value or retrieving a value from the stack is known as pop operation. So now if I say pop, let's say, so I say pop into register R1, let's say. So what happened that, remember, stack pointer is now pointing to this location which is empty, right? So first the stack pointer will be decremented such that now it will point back to this location, and then the value will be read from this location and put in the register 4 in register 1. So this is what we have here in next slide. Sorry, I have cough today. Sorry. So push instruction. So what we do is when you say push RR, so what happens? You are saying put the value of the register R on the stack. And what happens behind the scene, that first the value of the stack pointer with value of the location which is pointed by the stack pointer, that value from that location is put into the register. Remember, stack pointer is a register which holds the value, that value is treated as a memory address. So here you are basically saying get the value from the memory which is pointed by the value of the stack pointer register and put that value in the register R. Okay. And then as a part of the push instruction itself, what happens? That stack pointer is also decremented by 1. So you don't need to have a separate instruction to decrement stack pointer. On the opposite side, we have pop instructions. So when you say pop RD, so what happens is that first you increment the stack pointer. Why you increment the stack pointer? Remember, stack pointer always points to the next empty location, right? So you cannot pop anything from an empty location. So you must increment it. When you increment it, you move to the previous location, which holds a valid value. For example, here we when decremented the as a part of the pop operation, we first decremented the stack pointer. Now it points to the this location where we are holding the value of 4, and now this value of 4 will be popped out, and it will popped out and placed in the RD register. Okay. And these two instructions here, remember what we are saying. We are here. These two instructions we will be using in examples. That's why I want to explain them here. So here we are basically saying read the IO read from the IO address space uh, from the address of 0x3d and put the value in R28. 0x3d is basically address of your SPL register. So basically you are saying that put the value of the stack pointer low in the R28 register. And in the next instruction, you are saying put the value in R29 from the memory address 0x3e, which is basically the address of SP high, a stack pointer high register. So you are saying put the value of the stack pointer high register in R29. And R28 and R29 together, they are known as Y register. We will be using this Y register in examples. That's why in the examples, that's why I wanted to cover it here. Any questions? Yeah, I know. I mean, it's 8:45. I must stop here. Any questions before we leave? Do we have a lab this week? Let me check the schedule. So yeah, lab 4 is due this week, right? So you have a lab. So your lab 4 is due this week. So today is 9:30, right? So there will be a lab section, and if you have completed or you are need to work on your lab, you go to the lab room and you can show your work to TS. Mhm. Anything else? No? Okay, if not, then that's all for today. And please remember to fill that survey form. Thank you.